Alrighty, so here we have, it's a 0.2 gram flea, little tiny animal, bug, sitting at a distance of 5 centimeters from the center of a rotating LP record. Bonus marks for anyone that knows what the letters LP stand for. Excellent, Nate. Long play record. That is absolutely right. When records first came out, you could only put 2 or 3 songs on them. There was the little singles, the 45 RPMs. You talked about in the musical about 45s. The 45s are the little ones. 45 revolutions per minute is what the 45 refers to. 45 revolutions per minute. So it would go. Yeah. So 60 seconds. So the old-fashioned, these are like that's how old. My grandparents had 77 RPMs. They were great, big, giant records. The big ones that you had in musical that your mom and dad probably have in the basement or sold at a garage sale, those are 33 1/3. The ones that, like the Led Zeppelin albums, that kind of vintage kind of thing. So these are LP records. These are 77 RPMs. So what centripetal force must be provided by friction to cause the flea to maintain UCM? This is very similar to a flat curve. So rather than the car going around the curve, what's happening here is the curve of the record is going around and the flea's sort of maintaining motion on there. So how much centripetal force has to be provided by friction so that the flea goes around on the record and doesn't slide off? Okay. Oh, now before I do all of that, I forgot. I want to show you one other. It's sort of it's not a formula. It's sort of a new formula, sort of, kind of. Okay? So I just want to remind you of a couple things. So since T is equal to 1 over F, and what I did, you guys here have the sheet. I squeezed it in on the back. There's room. Okay? So if you want to just write this on the back, you can. Since T is equal to 1 over F, and F is equal to 1 over T, the textbook uses a couple other formulas that are just a slightly little bit different. So the one that I've given you, velocity is 2 pi r over T, right? Which is velocity is distance over time. The distance is the 2 pi r. The time is the period. I can replace the over T with an F. So 2 pi r F. Those are equivalent, right? So in other words, if for whatever reason you're given the frequency, you don't have to convert it to period. You can just use that. Does that make sense? Okay. And that is true for all the other ones as well. So when we've got A, which is 4 pi squared, Nate, pi is squared, 4 pi squared r all over T squared. This is the longest formula of all time. It becomes what? 4 pi squared r F squared. And similarly, if centripetal force is m 4 pi squared r all over T squared, that's equivalent to m 4 pi squared r F squared. Hey? It's ridiculous? Centripetal force. What, the length of that is ridiculous? Oh. It's an R. Good luck coming up with the magic triangle for that. Yeah, thankfully, because I shake my fist at the magic triangle users.
What is magic triangle?
No, I'm not showing you, Mustafa. Actually, no, I should show you. Actually. I know. It's got its use. I just think that for kids that are going on to grade 12 physics, I don't want people only learning how to do it that way. Okay. No, Billy's not here. I don't think we've had a day in the last month where everyone's been here. No, we've had days. Okay, so here's the flea. Okay, so what do we know? We know the mass. Now, some of you probably realized right away that the mass, Nate was asking how many grams in a kilogram. You probably realize that we're going to have to do a conversion here, right? So this 2 grams has to be converted to kilograms. So, oh, it's 0.2, thank you. So it's got to go 3 decimal places to the left. So that's going to be 0.0002, right? 1, 2, 3. Yeah. That's kilograms. And you're right. The 5 centimeters has to be converted to 0.05 meters. Is there another one? No, there isn't. But we do have to handle the 77 RPM. So I'm going to, just for the sake of showing you how those new formulas work, I'm going to convert that 77 RPM to frequency, right? Frequency is how many revolutions per minute or per second. Okay? What's that, Nate? You can convert it to period too as well if you want, right? So 77 RPM means 77 revs per minute in 60 seconds, right? And frequency is the number of revolutions per second. So equals, we'll call it X. You know what? We'll call it X. I'll call it F. It's how many revolutions per second. So I'm going to put frequency over 1 second, right? Cross multiply. What are you going to get? 60. Oh. 60F is equal to 77. So the frequency is 77 divided by 60, or 1 point. Yeah, well, you got it wrong. 1.28 hertz. The frequency is 1.28 hertz. If you do it Nate's way, which is okay, Nate, you're not getting the frequency. What are you getting? If you go period, you're going to go 60 divided by 77, and what is it? 0.78. I don't care which way you go. Flip it upside down. Go 1 divided by that. 1 divided by 0.78. The crazy things you learn here. Okay, so now let's do the actual problem. We've sort of taken care of that. So the question is, what centripetal force must be provided by friction to cause the flea to maintain its UCM? So we are looking for the centripetal force. I'm going to use this new one. M4 pi squared RF squared. Hertz is HZ. Hertz. HZ. So that's going to be 0.0002 times 4 pi squared times 0.05 all over. Oh no, I did the other one. Not all over. Times 1.28 squared. Should it be a big number or a small number? It should be small, right? How much force is going to be needed to maintain this flea? Pretty tiny. No, I'm not going to be mean. When have I ever been mean? You'll get it wrong. Is that what you got? 0.065? 0.0065? I had that when I was well, you could have, instead of multiplying by 1.28 squared, you could have divided by that 0.78 squared. That works too, actually. Yeah, that's a long way to do it. But so not particularly challenging, just long and weird formulas, and just more than anything, a reminder about watching units, right? Grams and centimeters, how to handle something like 77 RPM. That's more about that, what that problem is. Should I pause there for a second? All right, so let's have a look. I'm just going to make this a little bit smaller here so I don't waste so much space on the question. Come on. There we go. Okay, so we have a chestnut. I always laugh at this question. Chestnut with a hole drilled through its center, hanging from a long massless shoelace. What does that mean, massless shoelace? It means just ignore the mass of the shoelace. Don't worry about it. Because actually that does change things, because the mass of the shoelace matters, but the mass isn't at the end. There's actually mass all along, right? And so the mass of the shoelace has different radiuses than the chestnut. So a bit of a calculus question for you. I'm not going to worry about it. Child spins a chestnut in a vertical circle at a speed of 4 meters a second. The shoelace is 0.8 meters long. Determine the tension in the string at the top and the bottom. Now, it should be noted that this 4 meters per second is the average velocity, because we already know that it's going faster at the bottom and slower at the top. That's what we did the other day, right? Okay, so the centripetal force is equivalent to the net force, right? Which is made up of the tension plus the, can I move that? Which is made up of the tension plus the weight force. And again, the directions get a little wonky here. If you get stuck, if something doesn't seem quite right, make sure that it's more force at the bottom, less force at the top. Okay, so centripetal force, mv squared over r. So that 250 grams has to be converted to 0.25. The velocity was 4 squared, radius 0.8. You get a convenient 5 newtons. We need 5 newtons of centripetal force. At the top of the circle, weight provides some of that. At the bottom of the circle, additional tension in the string has to provide that. The weight force is mass times gravity. So 0.25 times 9.8, 2.45. Technically, I guess that is negative, right? Because it's down. 9.8 is down. That's the easy part, right? Now it's how do you put it together to make sure it makes sense. Okay, so at the top, this net force is the tension plus the weight force. So that net force has to be, now at the top, the centripetal force is directed down, so it's going to be -5. We are solving for tension in the string, and the weight force is also negative. Oops, put the decimal place in the wrong spot. Right? So that -2.45 goes to the left, becomes positive, and you end up with a tension of -2.55, right? Easy enough. What's different on the bottom? It's exactly the same thing. There's only one small change. I'll do it in blue at the bottom. Yep. Right? The net force, again, is the tension plus the weight force, but that 5 is up, right, at the bottom. So it's going to be +5, solve for tension. This, again, is -2.45, goes to the other side, and you get a bigger tension, 7.45 newtons. Generally, tension isn't shown with a direction, but I'm not going to get too excited about that this is a negative right here, right? Relatively straightforward. Just another example of a vertical one. Not that hard. Okay? There are some decent textbook questions if you want to attempt them. I know. Just giving you more. Some people like doing these for fun, you know, Nate. Some, I don't know who these people are, but if you want to try page 226, 15 to 25, I think I have solutions for them as well. I'll look and see. It wouldn't hurt you to try a couple of them. Okay, I'll stop talking. I'll let you work today. Tomorrow, Flying Pig, it's about a half an hour, maybe 40 minutes, so in the other classroom. Then you'll get time to work tomorrow as well. So have a great day.